Hello everyone, Mr. Fawcett here, and we are back with another AP Calculus lesson. Today's topic is the second derivative test. Now, in our previous lesson, we talked about how the second derivative could tell us whether the original function was concave up, concave down, or whether there was a point of inflection. Today, we're going to see how the second derivative can tell us whether the original function has a relative minimum or a relative maximum, or neither. Maybe it'll be what we call inconclusive. So we're going to start off with a little diagram. We're going to talk our way through the test, talk about the different concepts and ideas, and then we'll formalize it on the next page. We're going to start off with a graph. We have a graph of f of x, just a simple parabola. And we have this point, x equals a. And at x equals a, we can see that there is a relative maximum. And there's going to be a horizontal tangent line here. So let's think about what we know. If there's a horizontal tangent line, well, that means the derivative at that point, f prime of a, should be equal to 0, because there's a horizontal tangent. Slope of a horizontal tangent line is 0. Now, what can we say about the second derivative? Well, if we just take this interval from where I drew the function, what's going on with the second derivative over that entire interval? Well, again, if we think about the first derivative, if we think about these tangent lines, they start off positive. Those are not great tangent lines. They start off positive. They become less positive, right? They eventually end up with a slope of 0 up at the green point, and then they change to negative, and they get more and more negative. So the derivative here is decreasing, right? It's going from something that's very positive, the slopes of the tangent lines are very positive, then they gradually work their way down to 0, and then they gradually get more and more negative. So if the derivative is decreasing over that entire interval, well, we're going to know that f double prime is less than 0 over that entire interval. That includes at x equals a. So it's negative over the entire interval, which means that it's going to be negative at x equals a. Well, here's the first part of the second derivative test. We have a relative maximum. The derivative is equal to 0, and f double prime is equal to 0. Well, let's see what happens if I have a relative minimum. So I put a new function up there. We'll call this g of x, so it's different than the graph on top. And you'll notice that it has a relative minimum at x equals a. So we're going to have a horizontal tangent line at x equals a. Well, if we have a horizontal tangent line, that means the derivative g prime of a is going to be equal to 0. And if we think about the second derivative, on this entire interval, my derivative starts off negative. It gets closer and closer to 0. And then it becomes more and more positive. So the derivative is always increasing on this interval. Well, if the derivative is increasing, that means my second derivative, g double prime, is going to be greater than 0 on this interval. And it's greater than 0 on the entire interval, which means that g double prime of a is also going to be greater than 0. Right? If you're not understanding why g double prime is less than 0 when f prime is decreasing, or why it's greater than 0 when g prime is increasing, think about the relationship with functions and their derivative. Right? If a function is decreasing, the derivative is going to be negative. That's the same relationship between the first and second derivative, right? Because they're one more than each other. Right? If the original function's decreasing, the derivative's going to be negative. If the derivative's decreasing, well, the second derivative will be negative, and so forth. So here we have the first derivative equal to 0, the second derivative positive, and this is a relative minimum. So these are the first two parts of the second derivative test. If we have a first derivative that's equal to 0, well, we can start writing this out here. If f prime of a is equal to 0 and f double prime of a is less than 0, then f of a is a relative maximum. And the other way, if f prime of a is equal to 0 and f double prime of a is greater than 0, then f of a is a relative minimum. There's also a time where f double prime could equal 0, and that's the third part of the second derivative test. If f prime of a equals 0 and f double prime of a is equal to 0, then test is inconclusive. I should have told you don't really need to copy this down because it's on the next page, but it's not going to hurt to write it down twice. Might remember it better that way anyway. All right, so there's three possibilities when the first derivative is equal to 0, and each of those possibilities leads to a different conclusion. One where we have a relative maximum, one where we have a relative minimum, and one where we are unsure of what is going on with the function at that point. Okay, let's move on to the next page. All right, so let's formalize what we just talked about up above. So the second derivative test. Given f prime of c equals 0 and f double prime exists, if f double prime of c is less than 0, then f of x has a relative maximum. On the contrary, if f double prime of c is greater than 0, then f of x, but a has a relative minimum. And if f double prime of c equals 0, then the test is inconclusive. I could spell inconclusive, right? Inconclusive. So you may be wondering, well, why is that possible? Or how is that possible that the test could be inconclusive? Well, we're not going to get into it too much in this video. However, I would encourage you, if you're interested, as a little extension activity, check out these three functions. F of x is equal to x to the fourth power. We'll say g of x is equal to negative x to the fourth power. And we'll say h of x is equal to x cubed. And I want you to explore the derivatives and second derivatives around x equals 0. You'll end up finding that all the second derivatives at x equals 0, the value of the second derivatives are equal to 0, and the value of the first derivatives are also equal to 0. However, each of these functions is doing something different at x equals 0. One has a relative maximum, one has a relative minimum, and one has neither. So again, if you explore these, you'll see that it's possible for f prime to equal 0. But if f double prime is equal to 0, then we can't say for certain whether there's a relative max, relative min, or whether there is neither. So again, check that out if you're interested. I think it's a cool thing to think about, little extension of why the test is inconclusive when f double prime is equal to 0. Okay, let's start applying this test to some actual problems. So problem number 1. It says determine whether the function below has any relative maximums or minimums. If so, state where they are at. What I want you to do first, because I know we have other ways of determining relative maximums and minimums, I want you to first start off trying to find the relative maximums and minimums using the second derivative test. And if you get a second derivative test that's inconclusive, well, then you can revert back to your old methods of determining whether a critical point is a maximum, minimum, or neither. So pause the video, then come back and join us once you think you have solutions. Okay, so to use the second derivative test, we first need to find points where the first derivative is equal to 0. So I'm going to take the first derivative. F prime of x is equal to 4x cubed minus 12x squared. I need to find points where that's equal to 0, or x values. So 0, and I'm just going to start factoring. I'm going to factor out a 4x squared right away, so I get x minus 3. Well, that means my two critical points are x equals 0 and x equals 3. Now, for the second derivative test, I need to substitute those values into the second derivative, which means I need to find the second derivative first. So f double prime of x is equal to 12x squared minus 24x. Well, f double prime of 0, that's just equal to 0. Then I have f double prime of 3, that's equal to 12 times 9 minus 24 times 3. We get 108 minus 72, which gives me 36. So we have one x value where we can make a conclusion. That's going to be x is equal to 3. So f of 3 is a relative minimum because f prime of 3 is equal to 0 and f double prime of 3 is greater than 0. Now, we don't just want to give up and say, well, we can't conclude anything about x equals 0, whether it's a relative minimum or maximum. So we're going to dive back into our old methods of deciding whether critical points are relative minimums and maximums by using our handy number line. So I've got 0, I've got 3. I really don't care about 3. I know what's going on there. We know it's a relative minimum. However, we'll double check it just to make sure we did it correctly the first time. Let's choose, we'll go f prime, because remember this represents, this number line is f prime. Let's go f prime of negative 1. We'll go f prime of 1, and we'll go f prime of 4. I'm not going to put all the work up here because I don't have enough space. We can just punch these into our calculator and put the answers up. So I get f prime of negative 1 is equal to negative 16. So that's going to be negative. I get f prime of 1 is equal to negative 8. So that's also negative. And I get f prime of 4 is equal to 64. So that's going to be positive. So if we first look at x equals 3, our conclusion made sense. That is a relative minimum because the first derivative goes from negative to positive. Now if I look at 0, right, f prime goes from negative to negative. So this is neither. It's neither a relative maximum nor a relative minimum. If we wanted to think about the graph, we had a graph of f of x. If the first derivative is negative, that means our graph is decreasing. It levels off because our derivative becomes 0, but then it starts decreasing again. So there is a horizontal tangent at x equals 0, but there's no relative minimum or relative maximum. So we could stop there. The only relative minimum or maximum is going to be at x is equal to 3. Now you may say, Mr. Fawcett, why in the world are we doing extra work to figure out whether it's a relative minimum or maximum? Why don't we just start off with the number? Why don't we just continue to do what we're doing, right? And I could have used the number line to figure out what's happening at both of those critical points, x equals 0 and x equals 3, right? There's no need to find the second derivative. Well, you're right. For this problem, there wasn't a need. But there are some problems where the second derivative test comes in handy and where our number line actually can't be used. Let me take you to one of those examples. We're going to skip over these two. And we're actually right here at number 4. Let me give us some more space. So it says f of x is a polynomial function, and f prime of 3 is equal to 0, and f double prime of 3 is equal to negative 2. What can we conclude, if anything, about f of x at x is equal to 3? Well, we don't have a derivative to substitute values into, right? You could make a number line, plot your critical point 3, but there's no function to substitute in 2 or 4, right? Points on either side. So that method isn't going to work to figure out whether x equals 3 is a relative minimum or a relative maximum. So here we would have to use the second derivative test. So maybe read the problem again. Using the second derivative test, determine whether this is a relative minimum, maximum, or whether the test is inconclusive. Okay, first derivative is equal to 0. Second derivative exists, and it's negative. So we have f of 3 is a relative maximum because f prime of 3 equals 0 and f double prime of 3 is less than 0. So again, sometimes you'll have to use a second derivative test. Sometimes you'll have your choice of whether to use our old methods or this new method. All right, that is going to do it for the video. We'll go over the other problems in class as well as look at that chart below, although I would encourage you to look at that chart and see if you could fill in the relationships before we discuss them. They're just relationships between the original function f of x, the derivative f prime, and the second derivative f double prime. Otherwise, enjoy the rest of your day, and we will look forward to seeing you next time.